during the talk, please use the chat facility, and on the chat facility, send your question, if you will, to the host rather than to everyone. If you've got questions, use the chat to the host, and we'll pick those up at the end. We'll be muting everybody during the talk so that if your clock chimes or whatever, or the dog runs in, it won't spoil the talk for everybody else. But cameras will be left on unless you turn your own camera off. So at that point, can I invite Doran Swade, who took over on the 1st of January as the chairman of the CCS, to introduce the speaker. For perhaps one or two, it's worth saying that there is a certain irony that the CCS was, of course, founded now well over 30 years ago, and Doran, together with Tony Sale, were the co-founders of the CCS. And so it's taken us all this time to persuade Doran that he ought to take over the chair for 3 years of the society. So it's a real thrill after all these years to invite Doran to chair his first meeting for us. So Doran, would you like to introduce the speaker?
Thanks, Roger. Well, welcome to this event. It's a pretty novel one, and thanks go to Roger for the brainwave of actually extending the outreach of our program to the other side of the world. And of course, thanks also hugely to Barbara for being game enough to join us with this time dislocation. Barbara has degrees in prehistory and in public history, as well as qualifications in museum studies, which is an interesting and unusual combination. She's held several curatorial posts and is currently curator at the Monash Museum of Computer History at Monash University in Australia. Barbara manages the collection and researches computer history, and her research interest led her to her work in Trevor Pearcey, who had a very close connection with Monash. And it's about this work and the place, perhaps to some extent, in the larger context of Australian computing history that Barbara is going to speak to us today. So a warm and huge welcome to Barbara for joining us.
Okay, welcome. I'm very pleased to be talking today. So I'll click on shared screen. Okay, is this all good?
Excellent.
Okay. Okay, I'm very pleased to be talking to you. Well, it's for the evening for me, but it's morning for you. But it's a really good use of Zoom to be able to contact people in England and see them for the first time. I've known and spoken by email to many people, but I'm very pleased to be able to actually see you on Zoom today. The history of digital computing in Australia can be traced back to one remarkable scientist, Dr. Trevor Pearcey. He proposed a project in 1947 that would create the first digital computer in Australia. Trevor Piercy, Maston Beard and their team ran the first successful tests on their computer designated CSIR Mark I in November 1949. It was an electronic digital general purpose computer with stored programming. The team worked in relative isolation in Australia. I would like to talk about the work of Trevor Piercy, his role in developing computing in Australia, and the story of his computer, CSIR Mark I, which became later to be known as CSIRAC. Dr. Piercy finished his career at what is now the Caulfield campus of Monash University. I started researching the history of Dr. Piercy initially because of his connections with Monash University, where we have a museum of computing. Monash Museum of Computing History is in the Faculty of Information Technology and is located at the Caulfield campus of Monash University, Melbourne, Australia. Monash University has several campus locations in Melbourne as well as internationally. It received its charter in 1958 and the first campus was located at Clayton. A separate teaching institution at Caulfield was amalgamated with Monash Clayton in 1990. The Caulfield was an older school established in 1922 and had a changing organisational structure, but they were joined together in 1990. Both schools had an early association with computing from the 1960s. The Monash Museum of Computing History is an initiative of the Faculty of Information Technology and was started in 2000. We have a small team with our director, Associate Professor Judy Sheard. I'm the curator. Chris Avram is an honorary research associate, and Professor Graham Farr also contributes to museum activities. And here we are looking splendid in front of CSIRAC at Melbourne Museum some time ago now. In the collection, we have one of the first computers used on campus at Monash, which is a Ferranti Sirius installed in 1962. And this is on display here. In 2000, our director, Judy Sheard, realised that like most institutions, Monash University had rapidly changing IT installations, and the fast evolution of computing has encouraged rapid discard of technology and focus on the latest and next development. She decided to create a museum of the history of IT at Monash. The museum has a permanent home in Building B Caulfield campus with a display and storage space. We also research the history of computing at Monash, and this includes people as well as hardware and software and activities by people associated with computers at the university. Among the early staff in the university's history was Dr. Trevor Pearcey, who held different positions at Caulfield campus when it was still a separate institution. He was on staff from 1972 until 1984, when he retired as Foundation Dean of the Faculty of Technology at Chisholm Institute of Technology, as the Caulfield campus was then called. This connection between Pearcey and Monash started my work on the biography of Pearcey and his computer career. He arrived in Australia at the turn of 1946 and immediately started looking at introducing mechanical computation. He brought new ideas and started a transition to digital computing. When he arrived, there was a limited range of mechanical computation in Australia. Some of the early developments of electromechanical developments existed, and there were also imported data processing machines. Before the introduction of digital electronic computers in Australia, a major figure was Sir George Julius, who designed an electromechanical machine that he initially hoped would be suited to be used in vote counting. But when this was rejected, he applied his ideas to a machine to calculate betting payments, known as the totalisator. This was based on betting, where the house takes a set fee, also the government got a percentage, and then all money is distributed to the participants. Julius's first totalisator was installed in New Zealand in 1913, and he formed a company called Australian Totalisator Limited, which was a commercial success. The work of Sir George Julius was innovative during the first half of the 20th century, and he was also to have a major impact in government research by his encouragement of science and engineering. The Australian federal government created a new body in 1926 called the Council for Scientific and Industrial Research, or CSIR, to undertake research, and Julius was the chairman until his death in 1946. The council was later renamed the Commonwealth Scientific and Industrial Research Organisation, or CSIRO, in 1949, as it still is known, and this group established specialised divisions. There were other developments around before 1940, including calculator designs and mechanical device known as an intergraph, built by David Milton Myers at the University of Sydney. Myers had completed his engineering studies at Sydney prior to going to England in 1933 and completed his doctorate at Oxford, where he worked with Professor Douglas Hartree on building a differential analyzer. On his return to Sydney, he built a machine he called the intergraph, And this was a device used as a graphic solution of commonly occurring second-order differential equations. And there's quite early footage of this on YouTube showing how this machine worked. The early use of the term computers was usually applied to mathematical staff, often women, completing calculations with analogue equipment. The first notable use of women computers in Australia was their participation in the Astrographic Catalogue Project, which was an international project created to map the night sky through photography, starting in the late 19th century. Several Australian observatories were involved from 1890, and some women were even employed up until the 1960s. The female computers completed astronomical calculations, and they were employed to measure, log, and calculate the position of stars using a micrometer. It was extremely intensive work and very hard on their eyes, but they were paid quite a good wage, so they continued on with this work. Large numbers of women were employed as computers during World War II as well. In the mid-1940s, the CSIRO, Division of Radiophysics, had a group of female computers supplied by the Air Force to process data reduction work, recording super refraction events reported from 112 radar stations around Australia. They had access to some contemporary desktop calculators. Women computers also played an important role at the long-range weapon research sites in South Australia from the late 1940s, which was working at Woomera and in Salisbury in South Australia. This work involved testing rockets in the desert and reducing the data for an analysis, which was then sent to England. The female staff in South Australia worked on rocket telemetry, initially using hand-operated desk calculators, and later transitioned in operating digital and analogue computers. This group was led by Mary Whitehead, seen here on the left in the centre photograph, with her warm clothing for the desert. Also, this was the modest clothing for the girls to wear out on site. There were 3,000 men at Woomera and very few women, and they tried to dress them up in the blandest outfit they could find. Punch card technology was introduced in the 1920s into Australia, which was part of the sales territory covered in the British Tabulating Machine Company's lease of Hollerith technology from IBM. As such, IBM did not sell their tabulating equipment in Australia until after 1948. The earliest uptake of tabulators was prompted by the work of the Commonwealth Bureau of Census and Statistics, and they first used Hollerith machines in 1921. They continued to supply Hollerith machines for the Bureau into the 1950s, and the 1961 Australian census was the last time tabulating machines were used for information processing of this data. In Australia, the business stationery company Kalamazoo secured the agency for Power Samus punch card machines, and they installed their first machine in 1923. Equipment from these two suppliers was used throughout commercial and government offices, and there was also desktop equipment as well from various different companies. During World War I, and later to a much greater extent during World War II, there were code-breaking groups working in Australia. Captain Eric Nave, an Australian cryptographer, led a local small Navy code-breaking unit based in the Victoria Barracks in Melbourne, and he was soon joined by other groups. American cryptography personnel were evacuated from the Philippines in 1942 and relocated into Melbourne, and they were reorganised to establish a new section called FRUMEL, Fleet Radio Unit Melbourne, as well as other different groups. They were stationed in this small block of apartments known as Monterey Apartments in Queens Road, in just out of central part of the CBD of Melbourne. It was an ordinary block of apartments taken over for this purpose. British specialists were also evacuated from Singapore and joined the group in Australia, and much of the activity was later moved to Brisbane. Significantly, the US personnel brought with them IBM punch card equipment, and this was applied to breaking Japanese codes. The machines were moved from Monterey in 1944 to new barracks at Albert Park Lake, which is just opposite this building. And this is in fact the site of the current Melbourne Grand Prix. They had 10 key punchers and 3 tabulators when they moved, and it ran 24 hours a day. This introduction to the use of the machines was significant for later Australian computer developments in code breaking. As well, the use of IBM machines in code breaking was significant as the staff who were working on these areas, when they later returned to their normal academic activities, they had a newfound appreciation of the potential uses of punch card machines. At the end of World War II, the use of radar was also quickly taken up in the war effort in Australia. The CSIR created Division of Radiophysics in 1940. It was a slightly misleading name for what was in fact a secret radar research and development group. It was located on the grounds of the University of Sydney and shared a building with the CSIR's National Standards Laboratory. The group had a research team of physicists, which were later led by a Welshman, Edward Bowen, known as Taffy. Bowen had worked on radar in England and was part of the Tizard mission to the US in 1941. He stayed at MIT for nearly 2 years and then accepted a position at Radiophysics in Sydney in 1944. Another engineer working with CSIR was David Milton Myers, who I previously mentioned, and he was interested in analogue computing devices and was part of the National Standards Laboratory. The Radiophysics Division combined both research and practical work with a skilled workshop to produce the radar equipment in-house. They were familiar with valve technology. It's worth noting that research staff in Australia often had connections with overseas institutions. Bowen was well known to both English and American science circles. Many Australian physicists and mathematicians had completed their PhD studies in the UK in the pre-war years, as Australian universities did not begin to grant doctorates until 1948. There were many Australian and New Zealand graduates working in the UK still. This formed a network of interconnected scientists at many levels, especially in the upper levels of the CSIR staff. At the end of World War II, the Division of Radiophysics started looking towards its post-wartime research program. Dr. Bowen set out a strategy for the division, and this focused on radio astronomy and cloud physics, or rainmaking, as well as radar propagation. As part of this strategy, CSIR advertised for a physicist to work in radiophysics as head of the mathematical section under the propagation committee. After some correspondence, a young Englishman, Trevor Pearcey, was appointed to this position, and he flew to Australia via the US in late 1945. Trevor Piercy was born in Woolwich, England in 1919 and attended the Imperial College of Science and Technology, London from 1938. He graduated in 1940. His family were not academic, but were in fact commercial barrel makers for the oil industry. He was interviewed for the job, and correspondence with the Australian office noted in his interviews he mentioned his great interest in mechanical computation. With Britain's wartime commitments, Pearcey had not continued studies for a doctorate after graduation, but began work for the Department of Supply, and he later moved to the Air Defence Research and Development Establishment in Great Malvern. From 1940 to 45, he undertook research in the theory section. They produced regular papers in their work, and later Pearcey was able to publish a paper in 1946 directly based on his work from this time. And the calculation that he published is now named the Pearcey integral. Pearcey's work required large amounts of calculation, and this brought him into contact with Professor Douglas Hartree and his team at Manchester University using their differential analyzer, as well as the one at Cambridge. Pearcey was also acquainted with L.J. Comrie and the use of punch card machinery for data processing. He was not aware of Bletchley Park computer developments. Upon accepting his appointment in Australia and organising personal matters such as getting married, Pearcey travelled to Australia in late 1945 and flew initially to the US for several weeks. He took the opportunity to visit several installations in the US, including the Automatic Sequence Control Calculator, or Harvard Mark I, which was an electromechanical calculator developed by IBM. Pearcey met its designer, Howard Aiken. He saw also the current Bush differential analyzer at MIT. However, he did not see ENIAC, which was still classified as secret in December 1945. Upon arrival in Sydney, Pearcey began to work at the Division of Radiophysics in January 1946. He set to the task of producing the large amounts of computation required by the research staff in radiophysics, which by this date was concentrating on the new field of radioastronomy. Pearcey led a computation group consisting of 2 research officers and about 6 to 8 female computer staff. They had increasing amounts of data to process. During the war, the number of female computers had been supplemented by the Air Force female staff. However, few of them wanted to continue the work. The division started employing new female staff in 1946. During the filming of a 1946 movie promoting the work of the divisions, there's a sweeping shot of the room, and you can see these women working in this office with various different types of mechanical desktop calculations. I have had an acquaintance look at this photo, John Wolfe, and he identified some of the machines, which I thought was very good. They're very hard to see. They also had acquired some punch card equipment, but another group at the section of mathematical instruments in the adjoining National Standards Laboratory was working on mechanical computation as well, and David Myers, who led this group, decided to build a differential analyzer. After spending just about a year in Sydney, Pearcey proposed a radical new idea that the division should build a digital general-purpose high-speed electronic computer with stored programming. Surprisingly, SIR agreed to Pearcey's suggestion. They were quite enthusiastic, in fact. He first put his ideas on building a digital computer together in an internal paper for the division in late 1946 entitled Modern Trends in Machine Computation. And there is a draft form of this in the files at the National Australian Archives, which I've fortunately found. It's a 50-page discussion on existing mechanical computation available and some description of major developments, including ideas on memory storage devices. It then goes on to describe a proposed electronic computer in an appendix with the title, The Organic Structure of a Computer on the Successive Principle. This is I've just included a small diagram just to show it was fairly, the diagrams were fairly handwritten and simple amongst the paper is a typed document with errors, and it's obviously quite an early draft of his paper and his ideas. The report's survey of existing knowing machines indicates Pearcey had read current journals. However, Pearcey appears to have also had access to a 1945 paper written by Douglas Hartree. Hartree was familiar with the US projects and had visited the US in mid-1945. Upon his return to the UK, he wrote up a 17-page description of current computing activities, the US developments in calculating machines, an informal and unofficial survey. It was marked confidential. The paper gives an overview of existing work and then comments on von Neumann's proposals for the logic development of the new computer EDVAC. Hartree's paper in 1945 was not publicly circulated. Comparison of Hartree's notes and the document written by Pearcey in late 1946 shows several similarities and some almost identical sections of text. There are no references given at the end of his 1946 paper, but the text clearly shows Pearcey was directly quoting from Hartree's 1945 notes. It's difficult to know when Pearcey would have had first access to this document. Hartree did show his confidential report to Maurice Wilkes in Cambridge in early January 1946, but only after confirming that it was acceptable with his US contact, Herman Goldstein. So it's hard to say when the information passed to Australia, but somewhere around late 1946, the notes were made available to Pearcey. However, Pearcey did not have access to von Neumann's paper on the design of the EDVAC at this date. And he knew of the paper, but he had not been able to get hold of it. The information in Hartree's notes started Pearcey onto a new direction from his first ideas to use punch cards and differential analyzers. He incorporated elements of Hartree's notes into his paper, but he gives no referencing, possibly because he didn't want the paper was still confidential and he didn't want to mention it. But he also said he knew of McCulloch and Pitt's 1943 article on logic, which is mentioned in von Neumann's paper as well. But he doesn't mention that in this 1947 paper. When Pearcey later described the start of his work on digital computing, he acknowledges the influence of Douglas Hartree and L.J. Connery. This may have started his interest, but Pearcey and his team went on to complete a working machine in isolation. Pearcey was the driving force for this new project. In 1947, he developed the logical design and then worked with CSIR engineers to build a working model designated CSIR Mark I. The machine was called CSIR Mark I on documentation at this date, but it was later renamed CSIRAC. Pearcey led the theoretical logic design, while Maston Beard, an electrical engineer, and his team designed the hardware and focused on the electrical and electronic aspects of the project. Pearcey recalled that they worked separately but combined their areas of expertise to complete the project. Reg Ryan, who worked on the Mercury delay line, recalled it was a very friendly, very cooperative, very much a scientific, technical team approach. The radiophysics staff had experience in radar and pulse technology, but had to resolve their own problems with little knowledge of overseas developments except what had been published. They were aware of Gold's research on Mercury delay line memory. They worked on solving issues throughout 1948. Work was impeded by industrial problems in Sydney at the time that led to power blackouts. The sudden power outs did not help the smooth running of a Valve computer. The CSIR Mark I was designed and built from 1947 onwards and was modified over its lifetime with some upgrades. It consisted of 9 cabinets with the 5 at the front held circuits, arithmetical circuits and memory control circuits. The 4 back rows of cabinets contained power supplies, input and output circuitry, clock and control row cabinets held power supplies, auxiliary store control circuits, a disk drive later, auxiliary test power supplies and memory control circuits. It weighed 2 tonnes and covered 40 square metres. The computer was entirely serial in operation with 20 bits per instruction and performed about 500 and later 1,000 operations per second. Early photographs give an idea of the appearance of the computer around 1949 to 1952. Input and output was initially via punch cards. It was difficult to get new paper tape equipment at this stage in Australia, and the group had to make do with an old column punch card reader and donate it to them. This proved unsatisfactory, and later they were able to change to 12-hole paper tape and an editing station. And also they had standard 5-hole paper tape later as well. The Mark I used about 2,000 valves and generated quite a great deal of heat. Its total power consumption was about 35 kilowatts. Cool air was blown through the cabinets from the basement below in the Madsen building, and this was continued in its later setup as well to keep the cool. You can see quite an early photograph of Trevor Piercy in the centre there with some older, this is quite an early 1951, 52 sort of shot of how they were having input. And the other photograph on the right shows Jeff Hill with Trevor Piercy. The primary store was the acoustic delay line memory of 1,024 words. This was provided by 32 metal tubes filled with mercury. Initially, each of these held 16 words, being constantly rotated, counted, and used when the counter matched the required address. Reg Ryan was given the job of building the memory. He had no knowledge of acoustic delay line memory when he started and had to find any documentation he could get hold of. He designed the tubing and crystals using metal and very carefully worked with mercury in a fume cupboard in the same room as the rest of the equipment, so it must have been slightly dangerous. He said he was very careful with the mercury. All the program instructions, he found that the initial memory capacity could be doubled by interleaving 2 16-word streams. All program instructions resided here, and data often would too. It was very important to maintain the temperature for these tubes. An additional tube, kept at the same temperature as the memory, generated synchronized timing for the control unit. The delay line memory had a cycle time of 1 microsecond. In addition, a magnetic disk was later developed by Brian Cooper and Maston Beard, and this provided 4 1024 word stores. As I say, they were developing the machine over the time of its life. Work progressed throughout 1948, and in November 1948, Pearcey visited England and saw the EDSAC being built at Cambridge. He was happy when he returned back to the team in Sydney to report they were working in the right direction and help confirm the CSIR's team's confidence in their existing logic design, and it was not thereafter significantly changed. In November 1949, Pearcey and his team at the Division of Radiophysics ran their first successful sequence of operations under program control. They did not record the exact date, unfortunately, but it's generally accepted to be in November. Later, Pearcey recalled it was completely homegrown, some 10,000 miles distant from the mainstream development in the UK and USA. It was the 4th or 5th computer built in the world. In his introduction for his doctoral submission in 1971, Pearcey wrote, "The general theory of bootstrapping, subroutine lineage, parameter parsing, and interpretive techniques, etc., were developed independently and were found to be similar in principle, subject to machine standards, to those developed by Wilkes, Wheeler, and Gill." CSIRAC had several teething problems, but Pearcey was able to demonstrate the machine publicly in 1951 and took on jobs for the CSIRO and outside users. Pearcey used the new computer for early simulations in fluid dynamics and rainmaking studies. It was also used for calculations for the Snowy Mountains Authority, which was a massive engineering project to use the resources of the Snowy River in New South Wales for irrigation storage and hydroelectricity. On a lighter side, CSIR Mark I was the first digital computer to be used to produce music. Paul Dornbush has investigated the story of CSIRAC's music. The exact date, like many activities with the machine, was not recorded properly, but occurred about late 1950. It was demonstrated publicly in August 1951 at the first Australian Computer Conference. The machine had a hooter or a speaker that could be used to track the progress of a program, and programmers would place a sound called a blurt at the end of their program so they knew it had ended, or they could program progress indicator blurts into a program. Jeff Hill, who had a musical background, realised he could program the computer to produce a range of tones on command. Years later, Pearcey recalled that the CSIR executive were not particularly impressed by this accomplishment, but it was used on open days to play popular contemporary music such as Colonel Bogey. There were no contemporary recordings of the music, but it has been recreated and is available if you'd like to search for it. It was a team effort. Pearcey and Jeff Hill worked together on the programming, and Jeff Hill was a valuable member of the team. Pearcey had also discussed many issues and his ideas on programming with John Jager, who was a mathematician and advisor to CSIRO. He was later Professor of Geophysics at the Australian National University, but he was an advisor, and Pearcey was able to sound many of his ideas with him. Pearcey regarded building CSIRAC as a research machine for developing programming techniques. He selected possible programs that would expand studies of programming. The engineering staff made an outstanding contribution. Led by Maston Beard, they tackled many issues. This is quite a nice photo of the three of the engineers in their building in the Madsen building room with the machine around them. Unfortunately, it's a little bit blurry. It's a 1950s genuine shot. I also think the other people who are rarely acknowledged were the staff in the radiophysics workshop who constructed the cabinetry and delay line tubes from the blueprints drawn in-house. In August 1951, the first computer conference was held in Australia at the University of Sydney. The main guest for the conference was Douglas Hartree. Myers, then head of electrical engineering at the university, invited him. It's interesting to look at this conference as it marks a watershed between analogue and digital equipment. Myers demonstrated his differential analyzer, but then Pearcey demonstrated their new digital computer to the conference attendees. There was some tension between the two men over their roles. Myers thought that mechanical computation should be under his department. He was also uncertain about the question of whether CSIRO should be involved with any electronic computer developments. Hartree visited Australia for several weeks, was the main speaker at the conference. While he was primarily lecturing on his work, the CSIRO also took the opportunity to consult him on the future of their digital computing project. Hartree was an old friend of Fred White, head of CSIRO, and they were in communication over the issue of what next for Pearcey's computer. Pearcey, aware of rumblings about the future of the project, also contacted Hartree directly and to seek his advice on how to keep the project going. This put Hartree in an odd position as he was giving advice to White and not supportive of the CSIRO continuing this type of experimental work. So he didn't quite know how to respond in letter to Pearcey, who was wanting him to say how to keep it going. Unfortunately, despite running well during the 1950s in the earlier part, the CSIRO was still not convinced that they should be involved with the development of electronic computing. The Mathematical Committee, under the chairmanship of David Myers, met during this period and explored the options of commissioning a private company to build a Mark II. However, the quotes were very expensive. CSIRO was now more focused on their rainmaking project with cloud seeding, and Edward Bowen had also turned much of his attention towards a new project and was working to secure finances to build a radio astronomy telescope, which he achieved with the construction of the Parkes telescope. Correspondence on the future of the computer between the CSIRO staff and Hartree also continued. They were also becoming increasingly aware of overseas machines with different architecture. Ultimately, Hartree gave White his advice that Sir Mark I was a good machine with interesting ideas, but felt the machine had taken too long to build, while other overseas developments had moved on technically. Bowen had also withdrawn his support by early 1954, and he'd lost faith in Pearcey's estimates of time for any project he was now working on. It always took far longer than he anticipated. In April 1954, the CSIRO decided to cancel the next stage of the computer project in-house, citing problems over budget and the speed of change in overseas computing. They decided to give the machine away. It was transferred from the division to the University of Melbourne with both funding support and CSIRO staff to help install and operate the machine. Frank Hurst was sent to pack it up. Everything was placed into a truck and then they drove the computer south to Melbourne. It was then put back together, spruced up, with the door panels being repainted, and was now renamed CSIRAC. The University of Melbourne ran computer courses and opened up the computer to both university, CSIRO and outside users. It ran as a sort of early bureau for Melbourne. It was used by research students, specialists and commercial users. There's some really interesting work done by students at this time, and probably we could go on some time about the interesting, there was work on meteorology and different aspects of producing programs to make weather forecasting over more than 24 hours. As at that stage, it was only possible, but it was a research facility. Staff made some changes to the computer and it was developed. In 1960, Jeff Hill devised a simple automatic language for CSIRAC entitled Interprogram, where programs could be written in an English-like language. CSIRAC officially commenced operations on the 14th of June 1956 at Melbourne University and was in use until November 1964. For that period, CSIRAC was switched on for 30,000 hours, during which time 700 computing projects were processed. There was a small team running the group, and Trevor Pearcey is visible on the left in that photograph of the group. And there are also, we're very fortunate. One of the people who worked on CSIRAC at this time, Peter Thorne, is listening. I saw him log on today. So he's also listening to this talk. And he was working as a young student, and then later as a member of staff, and then later his career at Melbourne University in computing. So this group there includes Kay Thorne, who's invisible in the photograph. She was employed as a technical assistant in the computer centre and recalled her work at Melbourne University. On a daily basis, the atmosphere in the computer centre was the most intellectually challenging and the most fun I have ever encountered in a workplace. We didn't accept limitations, just challenges. The University of Melbourne turned CSIRAC off in 1964 and then donated it to the National Museum's Institute of Applied Science Victoria, now called Museums Victoria, in March 1965. In the 1990s, a team at the University of Melbourne, led by Peter Thorne, who I just mentioned, and later staff at Museums Victoria, worked together to record the original equipment and documentation in their collections. And this material now forms the basis of the CSIRAC collection, with over 300 objects, 300 images, and 1,000 documents relating to the CSIRAC computer and Trevor Piercy. While the machine was mostly in storage from 1965, for several years, from 1980 to 1992, it was on display at Caulfield campus in the very same space as where our current Monash Museum display is now housed. It was then put back into storage before it came out again with work for the 40th anniversary of switching on of the CSIRAC at the university, where Melbourne University organised a conference in 1996 for this event. And this really stimulated a great deal of research and interviewing of personnel involved with the development of the computer. The conference led to an excellent publication, The Last of the First, edited by Doug McCann and Peter Thorne, who gathered information and interviews with early members of the staff who designed, built and used the computer. And this is now available online if you wish to download it. After some research and preparation, Museums Victoria then displayed the computer at Melbourne Museum until 2018, when once again it went into storage. But now sections of the computer are on display at one of Museum Victoria's exhibition spaces called Ainsworth, and it's part of a display entitled Think Ahead. This is a photo of the exhibition in 2008, when it was still part, there was a computer exhibition at that time at Melbourne Museum, which is in the centre of Melbourne. And CSIRAC was featured at this, later it was moved to a different position, but you can get an idea of it was quite nicely displayed at that time and set up with a lot more editing equipment than that first photo that you were seeing of Trevor Piercy. So while Australia had only one digital computer in the start of the 1950s, CSIRAC was soon to be joined by several installations based on UK and US designs. The University of Sydney built a copy of the University of Illinois' computer, which was known as ILIAC. They put an S in front of it and called it Sydney ILIAC or SILIAC. They didn't think too hard about the name, calling your computer silly. I don't know why they bothered. Anyway, Sydney had a new, young and dynamic professor of physics called Harry Messel. He thought CSIRAC was too slow for their proposed research program, and he found a donor to cover the cost of building a machine for Sydney University. In 1956, Sydney unveiled their new machine, SILIAC. Messel's comments also partially influenced the CSIRO's attitudes towards the future of SIR Mark I, which when he was looking in 53, 52, he was saying CSIRAC, SIR Mark I was a bit slow. Another university in Sydney, the University of New South Wales, installed a machine in 1956, which was designated UTCOM, as it was the University of Technology at that point. It was an English electric juice. And meanwhile, in South Australia, the Long Range Weapons Establishment, we had the ladies before, which was working on rocket developments at Woomera, had been looking at building their own version of CSIR Mark I in the early 1950s, but these plans were not completed. At the same time, John Ovenstone was sent to study at Cambridge with Douglas Hartree, and he came back and he recommended a special version of the Elliott Brothers 400 series. It was built in the UK and shipped in parts to South Australia in 1955-56. It was designated REDAC, as the group had now been called Weapons Research Establishment. They had a range of analogue and digital equipment at the Weapons Research Establishment and built on that from this time. And this Patricia Yates in the photo was one of those first female computers, and they transitioned to using all of this equipment. Another secret machine was sent from England in 1957 to be used at the Defence Department's Defence Signals Directorate, which had grown out of the cryptology work in World War II and was still based at Albert Park Lake. 2 Australians, including Trevor Robinson, were sent to England and helped finish a version of Colour Rob. Trevor had first familiarised himself with computers by going and looking at CSIR Mark I for a couple of months. The new machine in England was given the codename Infuse, but the staff in Melbourne, when it arrived, called it the Beast. When it was completed, it was installed into 24 racks with coaxial cable used for interconnections. It had 1,000 dual triode valves and needed 50 tonnes of air conditioning. It was difficult to program, and they adapted an IBM plug board. Trevor Robinson described it as having so much wiring that it looked like a pile of brown spaghetti. By the late 1950s, digital computers were beginning to enter the commercial world, with an IBM Service Bureau established in Sydney in 1958 with an IBM 650, and insurance companies were soon installing their own machines. From just 5 computers, there was a growing demand for research and commercial machines, and by 1960, there were at least 34 machines in Australia. Transistors became the new technology, and the old first-generation machines were replaced. Still, CSIRAC continued in use until 1964. Although disappointed by the CSIR's decision to give away his brainchild, indeed, I think it was a great blow, Pearcey worked on the CSIRAC in Melbourne before taking leave of absence and returning to England to work with Philip Woodward on the computer TRIAC in 1957. He later returned to Australia and moved to Canberra to develop a computer network for the CSIRO and their distributed offices, and also worked with Murray Allen at the University of Adelaide on a new computer called Sirius. Throughout his career, Pearcey gave lectures starting in the Maths department at Sydney from 1947, with probably the first classes on computation and the principles of programming in Australia. During his times in Melbourne, he also lectured at the university. Having missed the opportunity to undertake doctoral studies at the normal time in his career, he formalised his qualifications with a Doctor of Science in 1971 from the University of Melbourne by presenting 74 papers covering his career starting from 1943. After working in private industry, Pearcey returned to an academic life and finished his career, retiring in 1984 as Foundation Dean of the Faculty of Technology at Chisholm Institute of Technology, which is now the Caulfield campus at Monash University. He died in January 1998 in Victoria. For me as a historian, one of his interesting achievements was a publication in 1988 of the history of Australian computing. It's an invaluable record of how computer technology became established here, and he personally knew most of the major participants in this history. He also did other written historical pieces, and in 1984, Pearcey and Maston Beard wrote a paper on the beginning of CSIRAC. Trevor Piercy arrived in Australia in 1946, full of ideas. He soon became convinced of a new approach to mechanical computation. He proposed to build a digital electronic general purpose computer with stored programming when very few people were even aware of this new technology. Pearcey and the team at CSIRO were part of a new global community who were working on the development of digital computing in the late 1940s. However, they were isolated and worked on their project with limited resources and knowledge of overseas ideas. While others were still looking to analogue equipment, Pearcey started digital computing in Australia. He was innovative, committed, and was a major contributor to Australian technology and science over a long career. Trevor Piercy's contributions are commemorated through the activities of the Pearcey Foundation, which acknowledges the work of current researchers and practitioners, as well as developing a record of the history of computing in Australia. We are fortunate that his work in building CSIRAC has been preserved in museums Victoria. The development of the new digital computer CSIRAC opened up the possibilities of the modern computer age to Australia. And I think I'll finish there and join the group. So,
Doran, would you like to unmute and thank Barbara for the talk?
Sorry. Barbara, that was absolutely fantastic. I mean, such a meticulous and granular account of that development of Pearcey's work and the context in which it occurs. There were a huge number of questions I had before this that I was hoping to, most of them have been answered. There's one in particular, before we hand over to Roger to field the questions that have been put through the chat facility, was the question of the diffusion narrative, that how did the information, how did the knowledge of the new computing paradigm from the Moore School, from the EDVAC team, diffuse into the rest of the world? And you have an extraordinary example of Pearcey's machine, which was the fourth stored program computer, as I understand it, to have been built. And is it correct in saying that the primary conduit of that information from the Moore School to Pearcey was through Hartree? Is it the case that Hartree was the primary conduit to diffuse that information?
I would say that Hartree, his name comes up so often behind other people's work. You understand he was sending out information and encouraging, because Pearcey did meet him in 1944, 45, when he was doing his work in England. And he was, they did joint papers, as did David Myers, had a joint paper with Hartree with his differential analyzer work. So I often think that Hartree must have been very good at drawing out ideas in other people and encouraging them, and that he was able to sort of lay the ideas, the thoughts that he could manage to say without perhaps, things were confidential still at that time. And I think he must have been quite careful, but very good at encouraging other people and stimulating them to move on to the next stage of their thoughts. And I think Hartree is the most important person in amongst all of these areas of the work, especially with the computing in Australia at that time.
So, I mean, could we nail it down and say that that Pearcey knew about the von Neumann architecture through Hartree, that the connection was via Hartree? Or,
yes,
or
because
the
the 1945 paper that Hartree made does refer to von Neumann's work,
yes.
But Trevor Piercy did not have access to the original document. In 1947, he is writing to, they had a scientific liaison office in the US, and he's writing to the man there saying, I need to read this paper, can you get a hold of a copy for me? And I've seen the request, and he was at the response several months later saying, I cannot get you a copy. So he had limited access to von Neumann's ideas, but he certainly must have had some idea of it, because he did later refer to the McCulloch and Pitt paper, which certainly is in von Neumann's ideas. So and one of the strange things is, I don't know how he found that paper, because I cannot find a hard copy in Australian libraries from that time of that paper. So I don't know how he saw that either. So, you know, and it was only recently, probably in the last 12 months, that I found this 50-page document amongst the files at the National Archives. So every time you open a new folder, you find something new. And I was very pleased to find that, and then be able to compare it to Hartree's 1945 paper. That I've been talking to Mark Priestley, and he's been very helpful about that and letting me discussing these ideas with me. So.
Thanks very much, Barbara. That was absolutely terrific. I'm going to open it through Roger to the queue, to the rest of the question and answers, and I don't want to exploit my chairman's privilege by carrying on the conversation, which I would love to do. So Roger, if you've fielded a bunch of chat questions.
I have just a few chat questions, more would be welcome. One of them, Bob Geetrell asks Barbara, how much did CSIRAC change between its initial operation and going to Melbourne? Was it stable or was it being updated?
There were modifications to the machine throughout its existence. They were always updating it, and the engineers were able to change it. I think it was updated quite a lot in Melbourne after its initial transfer. So, yeah.
Can you just remind me? I'm sorry, I may have just not picked it up because it was a wonderful talk with a lot of detail in it. What were Pearcey's links to the UK? Was it mainly through Hartree? Did he come to the UK at some point after going to Australia?
Yes, he went in 1948 and visited. He went to see the EDSAC, and he also talked to Maurice Wilkes, and he went to Manchester University and saw some material there as well. Right. So he did, but they'd already completed quite a lot by that time, and they actually confirmed that their own ideas were all right and were comparable to the work being done in England. Although he had communication with Maurice Wilkes by letter as well. They did know each other.
Did Pearcey know, or did Pearcey contact John von Neumann? Did he write to him? Is there any correspondence?
No, I have not found any contact with him.
Right.
But there were people there was John Blatt at the University of Sydney, who'd come from the University of Illinois, which is the connection that they went later on. And so there were people moving around that may have seen von Neumann's papers as well. John Blatt was a physicist, yes. But he was using CSIRAC with CSIRAC 1 as it was then, and didn't get on well with Pearcey.
Philip Wardle has asked a question about the availability of electronic components in the post-war period. How easy was it in Australia to get valves and other electronic equipment?
Yes, well, some were made. There was a problem in the post-war era in that they didn't have a lot of money for exchange to purchase US dollars, and this did limit some of their ability to get equipment and delayed delivery. That they had to wait some time. And I mean, that's why they used an old second-hand punch card that someone donated, because they weren't able to acquire new equipment very easily at that time. And the valves they did obtain the valves, but that took some time, and it was difficult because of there was a lack of money to do the exchange into dollars.
The same problem existed in the UK at the same time.
Right. Oh, Peter Thorne's there. I've just noted that Peter Thorne's here, and Peter is much better able to answer questions technically about CSIRAC than I am. So,
if Peter Thorne would like to make some comments on this, we'd love to hear from you. Just press your space bar. Excellent.
Hello, and it's lovely to see faces of people I've seen over the years but haven't seen recently, and I hope you're all well and keeping fit. The components were actually the basic electronic components were locally sourced. In fact, we always say it's the most Australian-made computer ever was valve manufacturing was done in Sydney during the war, because radiophysics had established itself as really a very competent radar facility, particularly for tropical radar. And the transformers were wound here, and the valves were made here. The big problem that, and I recall this even later, was getting input-output equipment. I mean, I remember when it was in Melbourne, we wanted I think it was a Creed paper tape punch, and the delivery time was something like 4 months, because it probably came by sea and so on. So, but the engineers at radiophysics were very competent. In fact, when you look at the computer, it was actually very, very well engineered. It was what we would these days call mil-spec. And when I look at the baby, and also look at pictures of the Cambridge machine, it seems to me that they were effectively built not as a totally integrated machine. They were evolved machines, as it were. Components were plugged together. This was actually designed. We have all the original circuit diagrams. We have the metal bending diagrams. We have everything as an engine, very much an engineered machine. So when I was last at MMoCH, it looked, the Witch, it seemed to me, is a very engineered machine, if I can describe it that way. The modularly constructed and built, and CSIRAC actually looks rather like that. So they had lots of local competence, but the input-output equipment was another question.
Thank you. There's a question from Tim Lyons, who asks, Tim, would you like to ask the question about the lessons possibly for EDSAC and the EDSAC rebuild?
Yes, I was just wondering whether the technology and the way it worked was similar to the EDSAC in terms of the way the sort of electronic pulses work around the system and so on, whether it was similar to EDSAC, and if so, whether there's any sort of information or comparators that could be of interest to the EDSAC rebuild.
Should I answer?
I think, Peter, that's a question for you.
Yes. Well, first of all, fantastic for the EDSAC rebuild. Anything anybody can do to help you should be done. So I'd say that for a start. I think the technology is comparable. I'm not sure. I don't have a lot of detail about EDSAC, but as a serial mercury to ley line machine, similar vintage, similar era. We have to realize, of course, that CSIRAC doesn't operate, and we have no intention of making it operate, because we would destroy its originality if we did that. We would inevitably. But if there's material on the detail of EDSAC construction, we can certainly do some comparisons and see whether we can help in any way.
Can I add in something to that respecting EDSAC rebuild? Of course, we are not using mercury in the rebuild, so it's non-authentic in that sense. But as far as the circuits are concerned, I was quite interested. I picked up the book, the last of the first book, yesterday and glanced through, and I noticed there is actually a circuit diagram in there, quite a complicated circuit diagram of the sequencer, and I noted I must have a look at that to see whether there's anything we can draw on it. Of course, we've attempted to be as close as possible to the original EDSAC circuitry design technology, So if there's a difference from the way CSIRAC did it, well, that's because there was a difference between the machines originally. But it's a good point that perhaps we should look wider at CSIRAC and see what there is that we could pick up.
Yes, look, the Barbara in her excellent paper has mentioned Reg Ryan. I have a theory that Reg Ryan was what I think they call skunk works, in the sense that I don't think anybody told Reg that what he was doing was pretty pioneering. You know, isolated fellow suddenly told you have to build a mercury ley line storage system for a computer. He was a very young graduate at the time. I think they just gave him the job and expected him to do it. And he did, in fact. Along the way, worked out that by interleaving, he could actually double the capacity of the store. So it would be very interesting, actually, to look at comparison between the two machines built on opposite sides of the world with quite similar technology.
I know that when you were doing the, I think this is to Chris, I know that when you were doing the rebuild, in a lot of cases where things didn't, where you were following the original circuit diagram and it just didn't work and you had to alter the way you were doing things. I think you said that you had to sort of think yourself into the mind of the original builders. I'm just thinking that maybe some hints of the way mindsets would have worked in that era may emerge from the way that CSIRAC had to solve similar problems to the problems that you've had to solve.
Oh, I think that's absolutely right. Clearly, the environment in the two cases was different, and naturally we think in terms of what would Wilkes and his team have done. I around that time, I'd just left from living in Central Africa and remembered buying components, for example, to make things as an electronic enthusiast. And the trying to get hold of equipment was very, very difficult. And I remember being able to buy a piece of radar equipment on the surplus market, which took indeed 4 months to get to Central Africa, not least because it was held up in customs, but that was the way one had to work. But that's a digression. EDSAC wasn't like that. They were there with their feet on the ground in the midst of it all. But it's a good point that you do have to put your feet in their shoes.
Thank you for that. I don't have any more questions, I think. But Barbara, sorry, did I hear a voice?
Yes, could I chip in with one quick one just?
Yes, Doran.
While Peter Thorne and Barbara are still with us. There seems to be a gap in the literature in tracing the transition from using vacuum tubes as analog devices into using them as switching devices for computing. And there are repeated references to the influence of radar and the technology for controlling pulse circuitry. And this is hotly disputed by Birks, who says it had nothing to do with radar. It had to do with physics instrumentation. I'm wondering whether Pearcey's work, or your knowledge of Pearcey's work, shed any light on whether, given that he was in a radiophysics department, whether there was any connection and any transition or any influence between how we got from using vacuum tubes, analog devices, vacuum tubes as switching devices, and whether Pearcey's connection with radar sheds any light on that connection. Was any of the circuit design informed by a knowledge of the pulse expertise involved in radar?
Do you want to answer that, Peter?
Well, look, it's an assumption I think we've made. I don't think we have the evidence that it was, but it was an assumption that he was in what you might call a radar-oriented environment, and they obviously made it work. I've often wondered, looking at the British sequence, how much the Colossus, and Tommy Flowers and the Colossus theme ran either overtly or under the lap right through through the development through Max Newman, through Morris and so on. The fact that you could do these things and the fact that they had already been done, whereas and because it seems to me, referring to something that was said earlier, Wilkes was in everything. I mean, Wilkes was encouraging the building of the ACE. Sorry, Hartree. Hartree was encouraging the building of the ACE. He was encouraging also the Manchester work with Newman. He was advising. I think he communicated with Wilkes. He encouraged Pearcey. There was this sort of confidence almost that you could do this, even if people weren't told explicitly as to what had happened with Colossus. There must have been a confidence that digital electronics really was a possibility and really was achievable.
Can I just add, with Pearcey, he was at Great Malvern, and there was a considerable number of people at Great Malvern, thousands of young physicists. And I gather that they did in fact have lectures almost for staff on what they were working on. And I wonder how much information was being passed around during that time. And so that, they were, it was like a think tank of bright young people who were on the edge of lots of information. And I think they were sharing to some extent as much as they were able. I did get this, I think I've read that they were, they gave seminars on their work. So this must have stimulated a bit of certainly with the delay line memory, I thought that was perhaps where they would become more familiar with these things.
Simon?
May I address Doran's point about connection between analog circuitry and digital circuitry? Chris will correct me, but I think if you look at the binary adder of the baby machine, you see that it's in some senses almost analog because the various electrodes in a pentode were used, as it were, in a cumulative effect. So rather than purely digital, you were, as it were, accumulating or adding up voltages. That analog approach, I may say, didn't last in successive adders, but certainly was there in the first. I'd also say that engineers in TRE and places like that were used to solving all sorts of problems that involved pulse techniques. And indeed, if you look at the Williams-Kilburn tube storage, the handling of electrostatic charges relies a lot on amplification, analog amplification. So I would say that certainly in the Manchester developments, there's a strong connection between wartime radar pulse techniques, high frequency techniques, and digital computers.
Interesting.
Can I add to that, Simon? Radar techniques did rely heavily on analog technology as well as digital. So when we talk about the influence of radar, we've got to cover both fields, and the baby machine is, I would say, 100% based on radar technologies, both analog and digital.
Can I just add one? And I've been trying to find the actual line to read it, but I know that I think it's in the early British computer conferences book that was published some years ago, Jack Good is quoted in a discussion after a paper as, and the topic that came up was, given the relatively high rate of failure of valves, was it feasible? This is a discussion, I guess, in the 1946, 47. Is it feasible to think of building a machine with hundreds of valves in? Would it not always be failing? Jack Good says, in his wartime experience, providing you leave the valves turned on, such a machine, in his opinion, would be feasible. Now, he doesn't say where that experience was, and probably the great majority of the audience would not have known. Obviously, people involved with Colossus would have known what he was referring to, but there was a culture of not asking, but accepting comments of that sort. So I think that the expertise from both radar and Colossus and other sources was shared, but anonymized in the sense of the source.
A lot of nudge, nudge, wink, wink going on.
Yes, I mean, part of it surely was the confidence, the fact that people, that in some cases the sponsors or the supporters of projects could, although they mightn't have been overt about it, knew that such things were possible, that putting a couple of thousand vacuum tubes or valves together wasn't a silly thing to do, gave some confidence to them in recommending and supporting these projects.
Mm.
Even if they couldn't say why they knew that.
Yes.
If I remember rightly, Roger, Tommy Flowers said that he'd got a piece of kit with 4,000 valves in 1933 for his telephone work. But as someone pointed out to me, that was likely to be quite parallel. So it's not quite fair, but he would have experience of an enormous piece of kit and its reliability.
Yes. That's an interesting contribution as well. This sort of expertise was around, and was, sorry, as it were, it was being shared, the expertise such as it was.
Hmm.
I think
Sorry.
perhaps
Sorry, sorry
Charles.
if this is an obvious question that people.
I did leave a message on your chat.
But I'm just wondering whether, am I right in assuming that if you transition from a more analog sort of pulse type system, I mean, this is going back to Doran's question, if you transition from a more analog pulse type system to a more digital system, you would use far more valves, and therefore it's only when the thing becomes much more reliable that you can start thinking about doing that. Is that the case?
Well, if I may make a brief comment, you say analog pulse, digital pulse, but in terms of the response of circuits, thermionic circuits, and indeed passive circuits to high-speed pulses, the technologies were the same. You had to understand charge storage, rates of rise of pulse edge and fall, etc. And so the techniques were, as it were, merged.
I think what this points to is that there's a piece of work to be done here in actually trying to trace the connection by actually looking at the circuit designs and the transition, you know, to actually track down and join the dots up. What actually was the relationship between radar pulse, the pulse technologies developed for radar, and what was behind Birx's comment, completely denying that radar had anything to do with it, and saying it was to do with techniques that we used in physics instrumentation, which is why when I read Barbara's the synopsis of the thing, and I saw radiophysics, and I saw this was the fourth stored program computer to be built, and here's a man in the Department of Radiophysics. I thought, aha, here's possibly the missing link. I think what the discussion, this hugely interesting discussion has revealed, is that actually there's a piece of work to be done here. You know, the kind of folk who can actually look at the circuits and actually do a timeline and track the actual relationship between the evolution of from radar to what was the source of the digital circuitry. I mean, we know about McCulloch and Pitts. What actually, where did the stuff in the digital circuits come from, and what were the lines of influence? And I think there's a bit of a black hole here, which would be very useful to pursue.
May I comment? I'd say that one starting point would be to look at the MIT shelf of books that came out of the war, setting down all the techniques that had been discovered and found successful during the war. And for example, F.C. Williams was invited to MIT to write one of the volumes. Look at all those volumes, and that could reveal something.
You mentioned that the team that were asked to design the circuitry in the Robinson were asked to do it because of their experience of designing high-speed counters at Cambridge. So that would fit your instrumentation. So it could well be that you've got folks coming in from each direction. The other thing is, I think Tommy Flowers published things in the Post Office magazine. So if you get hold of the Post Office technical magazine of the time, you'll be able to get dates and threads of things working through and what he knew beforehand.
I think probably this is the point at which we give a final thanks to Barbara for the talk. The next two talks are for the CCS, which you're all invited to. There is a talk on February the 19th by David Greer, the distinguished American historian, talking about aspects of ARPANET and its influence on computer science. That's our February meeting. At the beginning of February, I think it's February the 3rd, it's on the CCS webpage, Martin Campbell Kelly, sorry, is Bob there?
Yeah.
Bob, sorry, your Manchester meeting.
Yep.
Can you remind us? Sorry, my mind went blank for a moment.
I don't know if Martin's is. Martin did a talk for the CCS in London a year or more ago about the history of ICL revisited. A lot of us who regularly go to the meetings in Manchester are ex-ICL. And we would love to hear about that. So I've invited Martin. We were hoping to invite Martin up to a meeting in Manchester. Clearly that didn't work, but I've asked him to represent nominally to the sort of the Manchester, the Northwest group, but of course, because of the way we do things these days, it'll be open to everybody. So anybody with an interest in one of the main, obviously, I suppose it probably is the main British manufacturer of computers in the 70s and 80s. Martin will be talking to us. I can't remember if it's the 3rd or the 4th or the 2nd, but early February. We'll send out an invite to everybody like we always do. So yes. Although it's nominally Northwest group, it's open to everybody.
Yeah. And
Second, thank you.
Second, thank you. Just to explain, the Manchester meetings, the email invite will include the Zoom link. You don't need to book for the Manchester meetings. You just need to make sure you'll get the email for it. And we do ask the BCS asks that you book via the Eventbrite site. If you would like to hear David Greer's lecture later in the month.
Yeah, I have to say the Martin Campbell Kelly one is an early evening one as well.
Yes, it's a 6:30, I think. 6. That notice again, the timing will be in the email. But anyway, thank you to Barbara. Thank you to Peter Thorne also for contributing his expertise on the history in the questions, and we look forward to seeing you all again at a future meeting. Thank you very much indeed.
Good. Okay. Bye-bye.
Barbara,
Thank you.
Many thanks.